Okay, so in the last video we talked about solving basic problems with Coulomb's law. And just to recap, Coulomb's law allows us to calculate the electrical force between two point charges, and that is equal to K Q1 Q2 divided by R squared, where Q1 and Q2 are the magnitudes of the 2 point charges, and R is the distance between the 2 point charges. Now, when I say a point charge, what I basically mean is an infinitesimally small point of charge. Okay, so for example, a balloon is not a point charge because that is like a whole big object. Things like, a proton or an electron or an alpha particle or a nucleus, those things can be treated as point charges in the sense that they're very, very, very small objects. And you can basically assume all of the charge is focused at that point. That's why it's called a point charge. Now, generally speaking, you need relatively complex calculus to be able to apply Coulomb's law in situations where you don't actually have point charges. And we're not going to do any like super crazy integral calculus, but basically what we're going to look at is we're going to look at a simplified situation in which even if you don't have a point charge, you can still get the correct answer using Coulomb's law. And so without any proof, okay, just take my word for it, without any proof, it can be shown using integral calculus that if you have a spherically symmetrical shell of charge, it can act as though all the charge was located at the center of that sphere. Okay, so if you imagine a perfect sphere and it has charge along the outside, let's say positive charge, but it could be negative charge, it doesn't matter. And you think of it as having like, bazillions of different point charges. Okay, imagine like billions or trillions of, electrons spread out across the surface of the sphere. Even though there's actually like a bajillion different point charges along the sphere, it can be shown using integral calculus. And again, we're not going to get into that because it's, too much for this class. But it can be shown that mathematically speaking, you can treat this perfect sphere as though all the charge is located at the very center. And why that works, again, is not really important, but we'll just go with it. Okay, so if you make that simplification, then you can use Coulomb's law to deal with problems involving spherical distributions of charge as long as it's like symmetrically distributed. Okay, and so what we're going to see now is we're going to see Coulomb's law applied to finding the electrical force between two spheres, which even though they're technically not point charges, you can still get the correct answer as long as there's spherical distributions of charge. Now, it's important that you understand that when you're doing those types of calculations, you know that R is the distance between the centers of the spheres. And again, for reasons we're not going to get into, if you have a sphere full of charge along the outside, you can treat it as though all the charge is located at the center. Even if there's not any actual charge located at the center of the sphere, mathematically you get the correct answer if you assume that. And so it's important that you remember that R is the distance from center to center. Okay, so just to show you a quick example of that. Okay, here we have an example that says a conducting sphere of radius 0.1 meters holds an electric charge of Q equals 125 microcoulomb. Remember, micro is 10 to the negative 6. A charge little q equals negative 5 microcoulomb is located 0.3 meters from the surface of big Q. Find the electric force between the two charges. Now, some textbooks write Coulomb's law with a big Q and a little q. I prefer, Q1 and Q2 because I think it's easier to like distinguish between the two. So let's say Q1 is 125 microcoulomb and Q2 is negative 5 microcoulomb. All right, we want the electrical force between the sphere of charge and a point charge that's 0.3 meters away from the surface. Okay, but remember when you're applying Coulomb's law, you have K, which is the Coulomb constant. If it doesn't say anything about the permittivity in the problem, which it doesn't here, you can just use the normal Coulomb constant, which is about 9 times 10 to the power 9. Then we have Q1 and Q2, so I'm going to do 125 times 10 to the negative 6. The 10 to the negative 6 is to convert from microcoulomb to coulomb. and then negative 0.5, or negative 5.0 times 10 to the negative 6 Coulomb. The distance that we care about, though, remember, if we have a sphere of charge, we're treating as though all of the charge is located at the center of the sphere. And so the distance from here to here, if it has a radius of 0.1, that gets us to the surface, and the distance from the surface is 0.3, that means this, totally missed that. That means that this distance right here is 0.1, and then this distance right here is 0.3. So the R that we should be using is 0.4 meters. And we're going to square that. Okay, and so I'm going to plug this into my calculator and see what I get. Okay, so 125 times 10 to the negative 6 times 5 times 10 to the negative 6 divided by 0.4 squared. And I get an electrical force of 35.2 newtons. Now, if you leave this negative sign in here, you're going to get a negative sign in here. Now, it's really important that you don't overthink the concept of a negative sign, okay? Because understand, charge is not a vector. Charge is a scalar. You can have positive charge or negative charge, and that just tells you what type of charge you're dealing with. Force is a vector. Okay, force has direction. And so there's a difference between putting a minus sign in front of the 5 and putting a minus sign in front of the FE. Because here we're indicating direction. Okay, so what is the direction of the electrical force? Well, it kind of depends. I mean, obviously it's going to be an attractive force, but are you talking about the point charge, or are you talking about the sphere? Okay, clearly the sphere is going to be attracted to the right, and so the sphere would feel a force to the right. The point charge, the blue point charge, would feel a force to the left because it would be attracted towards the blue, towards the big sphere. Okay, and so this negative sign right here, don't get too caught up on that negative sign because that doesn't really tell you anything. You have to actually think carefully about what that represents, because it doesn't necessarily represent direction. And also it depends on which object you're talking about, because the electrical force between the two are equal and opposite because of Newton's third law. And so, one force is going to be to the left and one force is going to be to the right, like I said. Okay, but that's how you do a basic calculation with a spherical distribution of charge. So pause it there if you need to look at that some more. Okay, and then here we just have the work for that calculation. Okay, and so what we're going to look at to finish up this video is problems with more than two charges. And I really hope that you don't see a ton of these problems on the IB exam, but just in case you ever do, I want you to be prepared for being able to do these types of problems. Okay, so in order to solve problems involving Coulomb's law with multiple charges, remember, Coulomb's law only allows you to find the electrical force between 2 point charges. So let's say you have 3 point charges, and you want to find the electrical force on one of those 3 point charges. Okay, if I'm a point charge, and there's 2 other point charges nearby, each one of those other 2 point charges is going to put a force on me. Okay, which means I'm going to feel 2 different forces. Okay, so if I want to find the net force on me, I'm basically going to have to add those 2 electrical forces. Okay, and so this is going to take us back to something that we did last year, which has to do with vector addition and Newton's second law, and vector components, and all kinds of fun things like that. And I'm only going to do a few examples because these problems can get kind of complicated and messy. And I really don't want to spend a ton of time on it, but I also want you to have seen these just in case it ever pops up again. Okay, which hopefully it doesn't, but it has shown up before on past IB exams, so I want you to be prepared. Okay, so we're going to start off with a simple one-dimensional problem. And here it says, in the situation above, find the magnitude and direction of the electrical force on, let's start with Q1. Okay, so Q1 is out here. Okay, it's on the far left. There's 2 point charges nearby, Q2 and Q3. Okay, each of these 2 point charges is going to put its own force on Q1. Okay, so when it says find the magnitude and direction of the electrical force, there's two electrical forces, one from each of the other two charges. So what it's talking about here is it's talking about the net electrical force. Okay. In other words, let's think of it like this. Actually, I'm going to change to a different color to make this show up better. So if I were to draw an FBD, a free body diagram for Q1, Q1 would feel a force to the left from Q2. Actually, let me just do it like this. Let me color code this. So let's make Q2 red, and let's make Q3 green. And then I'll do the net force in black over here. All right, so Q1 would feel a force to the left from Q2. Why? Because that's a positive charge and that's a positive charge, and positive and positive repel. All right. Q1 would feel a force to the right from Q3. Why? Because Q1 is positive, Q3 is negative, and so if I'm Q1, I feel attracted towards the right. So I'm going to call this F3, and I'm going to call this F1. Okay, and so what I'm going to do is I'm going to calculate each of these forces, and then I'm going to add the two together. All right, so watch how this works. F1 is going to be given by Coulomb's law. So that's going to be K Q1 Q2 over R squared. And so here I have 9 times 10 to the 9. Q1 in this case is 2 times 10 to the negative 9. Q2 is 1 times 10 to the negative 9. Divide by the distance between Q1 and Q2, which is given in the diagram as 2 times 10 to the negative 2 meters. Okay, so I'm going to plug all of this into my calculator. So I do, let's see, I do 9 times 10 to the 9 times 2 times 10 to the negative 9 times 1 times 10 to the negative 9, and then divide by the distance between them squared. Okay, and I get 4.5 times 10 to the negative 9 newtons, and the direction of that is to the left. Okay, now for the force from Q1 to from Q3 on Q1, I'm going to call that F3, and I would also use Coulomb's law to find that. And again, I would do K, so 9 times 10 to the 9. Q1 is still 2 times 10 to the negative 9, but now if I'm using Q3 as my second charge, I need to plug in negative 3 times 10 to the negative 9. Sorry, I'm running out of space here. Now, if you don't put the negative sign, it doesn't really matter in the grand scheme of things, because again, this negative sign doesn't indicate direction because charge is a scalar and not a vector. So this negative sign doesn't really affect the magnitude of our answer. But in any case, on the bottom we have R squared, and here the distance between Q1 and Q3 is going to be 2 times 10 to the negative 2 plus 4 times 10 to the negative 2, which is going to be 6 times 10 to the negative 2. Because 2 plus 4 is 6. That's the distance between Q1 and Q3. So again, I'm going to plug this into my calculator. 9 times 10 to the 9 times 2 times 10 to the negative 9 times 3 times 10 to the negative 9. I'm not even going to put the negative sign because it's not going to change my magnitude or anything. Divide by the distance between them squared. And I get 1.5 times 10 to the negative 5 newtons. Okay, so what have I found out so far? Well, I found out basically that Q2 is pushing Q1 to the left, Q3 is tugging on Q1 to the right, but Q2 is winning, basically. I can see right away 4.5 is bigger than 1.5, even though they're going in opposite directions. So how would I find the net force? Well, of course, the net force is just the sum of the forces, F1 plus F3. And when I go to add these, taking into account direction, I would put negative 4.5 times 10 to the negative 5 plus 1.5 times 10 to the negative 5. You might ask, why did I put a negative sign here? Because look at the direction of F1. It's to the left. It's acting in the negative x direction. That's what this negative sign represents right here. Okay, and so overall I end up getting 3.0 times 10 to the negative 5 newtons, and that is the overall net force. Wow, I lost control of my pen. That is the overall net force on Q1. And I'm not going to do it for Q2 because I want to move on to example 2, but you would do it in the exact same way. Okay, you would use Coulomb's law to find the force between Q1 and Q2. You would use Coulomb's law to find the force between Q2 and Q3, and then you would add those two vectors together. Okay, so pause it there if you need to look at that some more. Okay, so I'm going to do a two-dimensional problem, and I will probably never do one of these ever again because it's a big pain to do. But again, I just want you to have seen this before in case you ever see it again. Okay, hopefully I never have to do this problem again. I apologize in advance. Example 2 says, find the magnitude and direction of the electric force acting on the charge in the top left-hand corner. Sounds like a simple prospect, but let's see. Okay, just for simplification, I'm going to color code this. I'm going to say this is a green charge, this is red charge, and this is blue charge. Again, the only reason I'm doing that is so when I draw the FBD, you can see where each of the forces are coming from. Okay, so we are focused on the charge in the top left-hand corner. I'm going to call that Q1. Of course, it doesn't really matter what I call it, but let's say this is Q1. Let's say this is Q2, Q3, Q4. Okay, so I'm focused on Q1. First of all, I'm going to think in terms of a free body diagram, what would the FBD look like on Q1? Well, Q1 is going to be repelled by Q2 because you get two positive charges, and so there would be a force to the left on Q1 coming from Q2. Q3 likewise is going to repel Q1, and so there would be a force up coming from Q3 acting on Q1. Notice, by the way, that I've drawn that one longer. That is intentional. That force is going to be bigger because notice that the distances are the same between Q1 and Q3 and Q2 and Q1 because it's a square. But the green charge, Q3, has a bigger magnitude, which means the force is going to be bigger. And then finally, we have the red charge that is negative, and so that's going to exert an attractive force towards the bottom right, like so. And that one I probably should have drawn a little shorter actually, but I don't want to erase it now. Now, the issue is I basically have three vectors I have to add here. And when you're adding vectors, you have to worry about vector components. Okay, and so I'm going to write all this out, and I'm going to start with the blue charge. I'm going to use Coulomb's law to find the electrical force between Q1 and Q2, and I'm just going to call that F2. Okay, so Coulomb's law is K Q1 Q2 over R squared, so I have 9 times 10 to the 9 times Q1, which in this case is 2 microcoulomb, so 2 times 10 to the negative 6. Q2 is 3 microcoulomb, divide by the distance between them squared, which is 0.5 squared, because 50 centimeters, if you convert that to meters, is 0.5. Okay, so I'm going to use my calculator to do that. 9 times 10 to the 9 times 2 times 10 to the negative 6 times 3 times 10 to the negative 6 divided by 0.5 squared. And I get 0.22 newtons. Now, what is the direction of that? It's to the left. That means that force is in the negative x direction. And so if I want to be really clear about what F2 is, if I think in terms of vector component notation, F2 is a vector that has an x magnitude of 0.22, and it's acting in the negative x direction, and a I don't know why I said x magnitude, I meant x component, and a y component of 0, because no part of this vector acts in the y direction. And you'll see why we're doing that in just a second. Now I'm going to calculate the force from Q3 onto Q1. And again, I'm going to use Coulomb's law. That's K times 10 to the, or 9 times 10 to the 9. Q1 is still going to be 2 times 10 to the negative 6. Q2 is going to be 5 times 10 to the negative 6, divided by the distance between them squared, which is the same value because it is a square. And so again, I'm going to go to my calculator. Okay, so that's going to be 9 times 10 to the 9 times 2 times 10 to the negative 6 times 5 times 10 to the negative 6 divided by 0.5 squared. And I get 0.36 newtons. And that's just the magnitude of that force, because if you look at the FBD I drew, we can see the direction is clearly in the positive y direction. So this blue arrow on my FBD, if you look at this, this is my electrical force. The x component is 0, and the y component is 0.36 newtons. And now I have one more to do. I'm going to find the force. I'm going to call it F4. I'm going to find the electrical force between Q1 and Q4. The magnitude of that would be 9 times 10 to the 9. Q1 is 2 times 10 to the negative 6. Q2, in this case, which is Q4, is negative 4 times 10 to the negative 6. Although that negative sign doesn't do anything for me as far as the calculation goes. Now I have to be careful because R is not 0.5 anymore, because this is a square, right? And so actually I need to use the Pythagorean theorem to find the distance here. And so, you know, if you do 50 squared plus 50 squared square root, and you do it correctly, I just typed it into my calculator wrong. 50 squared plus 50 squared, the square root of that is about 70.7. Basically the distance here, the distance along either diagonal is about 70.7 centimeters, which is 0.707 meters. All right, so that is going to be my R value down here, 0.707 squared. And so I'm going to finish writing it up here because I'm running out of space. 9 times 10 to the 9 times 2 times 10 to the negative 6 times 4 times 10 to the negative 6 divided by 0.707 squared. I get 0.144 newtons. But, and here's a big but, is that in the x direction or the y direction? Well, really, each of those has a component, and so you have to be really careful, because if we want to find the overall net force, I really need to find the components of that force. Now, luckily, this is actually not difficult to do. Because it is a square, I know that each of these angles is 45 degrees. Okay, and so I can find both the x component and the y component are going to be the same value just by using sine and cosine. Okay, and so the y component would be here, the x component would be here, and both of these angles are 45 degrees. So f for x would be 0.144, wow, try this again, 0.144 newtons. I'm just going to erase that a little bit. F for x would be 0.144 times cosine of 45 degrees. In this case, it doesn't really matter if we use sine or cosine, because sine of 45 and cosine of 45 are the same thing anyway. and I get 0.1. Let's just call it 0.1, and not worry too much about the rounding. Newtons, and then F for y is going to be the same thing. You would do it with sine instead of cosine, but it's going to be negative because the y component is going down in the negative y direction. So that would be negative 0.1 newtons. All right, so F4 is 0.1 comma negative 0.1 newtons, and the overall net force I could just find by adding up my vector components. So I have negative 0.22 plus 0 plus 0.1. That's going to be negative 0.12, comma. My y components would be 0 plus 0.36 plus negative 0.1. So that would be 0.26. And then this is almost my answer. Just for the sake of sanity, I might want to stop here. But I basically found the components of my net force, and the question says to find the magnitude and direction of the electric force acting on the charge in the top left-hand corner. If you want to pause it here, I'm going to erase the right side of the screen just so I can finish out this problem. Okay, so just to finish out this problem, if I want to find the magnitude and direction given the vector components, then I would do it like this. So I'm just trying to erase what's on my screen. Okay, so what I would do is I would say, okay, so the overall net force is going in the negative x direction, so it has this much x, 0.12. It's going in the positive y direction, so it has this much y, 0.26. So the overall net force would be going this way. I can find the magnitude of the net force just using the Pythagorean theorem. That would just be the square root of 0.12 squared plus 0.26 squared. Before anyone asks why I didn't put a negative sign over here, it's because it doesn't matter. Whether that's negative 0.12 squared or positive 0.12 squared, it doesn't matter because the squared would cancel out the negative sign anyway. And so I will do that really quickly. 0.12 squared plus 0.26 squared, square root. And we get 0.29 newtons. And then the direction would be given by an angle. And so I could just use inverse tangent to find that angle. So that would be the inverse tangent of 0.26 divided by 0.12. And again, I go to my calculator. And if you're thinking right about now that I hope I never see a problem like this, I also hope you never see a problem like this because this is quite a lot. But just in case you ever do, there you go. Okay, the magnitude and direction of the electrical force acting on the charge in the top left-hand corner. The magnitude is 0.29 newtons. And the direction is 65.2 degrees. I don't know if you'd say like, north of west or whatever, but there we go. Okay, that is the answer to example 2. All right, so pause it there if you need to look at that some more. Okay, so hopefully that is by far the hardest problem you'll ever see with Coulomb's law. You should definitely, if you can do this type of problem, you should definitely be able to do other types of problems involving Coulomb's law. In the next video, we will get into it with the electric field and the concept of the electric field. As always, please let me know if you have any questions, and I'll see you guys in the next video.